We're going to continue our discussion about exploring data with tables and graphs by talking about graphs that enlighten and graphs that deceive. Graphs can be used in really good ways and really bad ways. So what we're going to do today is we're going to look at some common types of graphs that help us understand data. And we're also going to talk about some ways that graphs might be deceptive or misleading or just wrong. Technology is super helpful in creating all of these different types of graphs, but a lot of them you can also make by hand. Now, I want to go with the caveat into all of this is that most of the graphs that we're going to talk about today can be done well and they can be done poorly. So it's important to make sure that you're using them in a way that you're compiling them in a very good way so that they're actually useful and they're not deceptive. So the first type of graph that can be incredibly enlightening is a dot plot. A dot plot is a graph of quantitative data where each value is plotted as a point above the horizontal axis, and the dots are stacked up on top of each other if they represent the same value. So a dot above 70 on this dot plot represents a pulse rate of 70. A dot above 90 represents a pulse of 90, above 82, a pulse of 82. So all of these dots here represent a data point, and each data point is the pulse rate of some male. So dot plots will only have a horizontal axis, as that's the only thing that we need, and you can see the frequency kind of like you could with a histogram just by how tall the stack of dots becomes. Dot plots allow us to see the shape of the distribution, and we can take a dot plot and we can make the original list of data values most of the time just from that dot plot that's provided. Another type of plot we have is a stem plot or a stem and leaf plot. This again represents quantitative data, and this time there's a vertical bar. In this case, it's split into a whole bunch of different vertical bars. Each line has a vertical bar. And on the left-hand side, there's the leftmost digit. That's called the stem. And on the right-hand side is the rightmost digit. So in this case, we have something like the number 40 split so that the stem is the 4 part of 40 and the leaf is the 0 part of the 40. And we can do this for all of our pulse rates again. And again, kind of like the histogram, we can kind of see how things are stacked up, but we don't get quite as much division without looking more specifically at the numbers. So stem and leaf plots, or stem plots, allow us to see the shape and the distribution of the data, and they retain the original data values. We could read out all of our original data values from our stem plot. Additionally, the sample data are arranged in order, so it's really easy for us to do other things with them once we have a stem plot created. Another type of graph that you might see is called a time series graph. In a time series graph, we take quantitative data that have been collected at different points in time, such as monthly, yearly, daily, hourly. It depends on the context on how often they will be gathered, and we plot that quantitative data point at each time that it's measured. So here we have year as our horizontal value, time will generally be our horizontal axis, and our vertical axis will be that quantitative data point. So in this case, it's law enforcement fatalities. So we can see that plotted over time. A time series graph allows us to see what kind of trends are happening over time, and this can be an incredibly helpful thing depending on what we're looking for. Yet another type, a bar graph. A bar graph can look a lot like a histogram. However, a bar graph is used to show frequency of categories or categorical qualitative data. Histograms are showing frequencies of quantitative data. So histograms create these classes for the quantitative data to fall within. And so they kind of are creating these categories by making those classes that a bar graph uses for qualitative data. Generally with bar graphs, you'll see a gap between the bars. However, that's not always the case. A bar graph shows us the relative distribution of categorical data. So it's really easy for us to compare between categories. The type of graph that you may not have seen before is called a Pareto chart or Pareto chart. People pronounce it different ways. All right. So this is a bar graph for categorical data, except what we do is the most frequently occurring category gets put leftmost, and then in order of decreasing frequency, they're listed. So the tallest bars will be on the left and the shortest ones on the right. What this allows us to do is, again, to see the relative distribution, so we can see between two categories which one's more common than the other. And because those tall bars are to the left, it allows us to, when we're reading left to right, to really hone in on those more important categories. So here's an example of one of these charts where we're looking at stolen boats and the type of boat that is stolen. So we immediately, our eyes move to those big ones, knowing that a jet ski and a motorboat are more likely to be stolen than, say, a sailboat. A pie chart is also a very common type of graph that depicts categorical data as slices of a circle. So each slice is a size that's proportional to the frequency count of the category. So to do this, we need that relative frequency value, that percentage, in order to know what percent of the circle each slice should represent. So this shows us the distribution of categorical data, and it's really commonly used, so it's something people are very comfortable looking at. So here's an example of a pie chart of the same data that we just saw in the Pareto chart, where you can see almost half of the boats that are stolen are jet skis. So a pie chart makes that type of thing very obvious to us. A word of caution, pie charts, a lot of times the wedges are not made the right sizes when they're published. So do be a little skeptical when you're looking at them to make sure that those wedges, the sizes of them, really truly correspond to the data that's available. The frequency polygon, this is a graph that uses line segments to connect points that are located directly above those class midpoint values. So if we took our histogram and put a point at the center top of every bar on our histogram and then played connect the dots with those dots, we would have what's called a frequency polygon. Right? So frequency polygons, we can also, just like with a histogram, have a relative frequency polygon. These are very common things. So a frequency polygon, here's one for that McDonald's lunch service time that we've looked at with the histogram. And this is what that frequency polygon would look like. And it, again, draws our attention to that most common midpoint time being 149.5 seconds. And it shows us that tapering off. Now, if we just use a frequency polygon, we can't compare to very easily unless we have the same number of observations. If we wanted to compare McDonald's and, say, Dunkin' Donuts as we have done before, we need to instead use a relative frequency polygon. We can put both of these on the same horizontal axis, and we can see the same way we could when we had the relative frequency distributions sitting side by side, how much further to the left Dunkin' Donuts falls than McDonald's. So we can see how much faster Dunkin' Donuts is than McDonald's in their lunch service times. So let's talk just a little bit about some common things that happen that make graphs deceptive. One of the most common ones is that the vertical axis doesn't start at 0. Not starting at 0 is a big problem. So here's an example of that. Say we want to know about whether a drug induces nausea or not, or makes people experience nausea. So we're looking at the drug Oxycontin. So when we look at Oxycontin versus a placebo, in the graph on the left, it looks like Oxycontin makes people experience nausea a whole lot more, like at least 10 times as much or as frequently as it does, or as the placebo did. However, if you look at the vertical axis, you'll notice that it starts at 10% and it goes up to just 24%. So it's not actually that wide of a range, and it doesn't start at 0. So the placebo looking close to 0 is actually above 10%. So if instead we start our vertical axis at 0, then we get the graph on the right, where we can see that, yes, Oxycontin does have a larger percentage of the participants experiencing nausea. However, it's closer to twice as frequently and not 10 times as frequently as the graph on the left would have us believe. So really look at those horizontal or those vertical axes when you're deciding just how extreme a difference is. Another type of graph that is often deceptive is pictographs. Pictographs are falling into this graphs that deceive category because it's very hard to do a pictograph well. However, you can use a pictograph in a very meaningful, good way. So I don't want to completely discourage you from doing it, but you have to choose very carefully what your picture is going to be and how you're going to situate it. So pictographs are used incorrectly and in a deceptive way probably 99% of the time though. So pictographs, what they are is a drawing of an object or objects put into like a bar graph type of dot graph type of thing, where instead of having just a dot or having some other type of graph, you have something that really grabs at the heartstrings of your audience. So if you're talking about money, you use dollar bills or coins stacked up, something where they are going to grab it. All right. So the problem with this is that those things, usually your data is a single value, making it one-dimensional. And pictographs, the things that you use for pictures, are usually 2- or 3-dimensional. Whenever you double the length of a side of a square, so it's kind of like you doubled the square, you're actually making the area 4 times what it was. If you have a 3-dimensional object, so you have a cube and you double the length of the side, you're increasing the volume by a factor of 8. So what happens is you end up with this idea that you were trying to show based on the length of a single side how things were, but when you scale the entire drawing, it ends up misleading. So here's an example of that happening. Here, again, use an object that pulls at heartstrings. We want to tell people about how many people are smoking. Use a cigarette. So in 1970, 37% of US adults smoked. And in 2013, only 18% of US adults smoked. That difference is about half. The cigarette on the left and the cigarette on the right, it's not half. It looks like it's about a fourth if you look at the area of that cigarette. But what they've done is they've made it half the length. So this is a way that it's good intentions. However, the outcome, because of the scaling of the drawing and using 2 dimensions, it's become misleading and deceptive. So if you use a pictograph, please be very careful. So some concluding thoughts. There are lots of graphs out there. We can't possibly talk about all of them in a single sitting, and I would really struggle to come up with a list of every single one that's out there, because graphs are a thing that we develop more of. The world needs ways for people to be able to look at data and make sense of it. And the graphs that we have are not all of the options that will ever be out there. People keep coming up with new ones. You might be the next person to come up with a new one. So just know that there are lots of useful graphs, and there are more useful graphs that will be invented in the future. Right. There are also lots and lots of deceptive graphs and ways that you can make graphs deceptive. We talked about a few of the ways today, but there are even more. So whenever you see a graph, be a little bit skeptical and make sure that it actually is truly representing the data. So there's this thing called the visual display of quantitative information by Edward Tufte, and there's these principles that he gives. So the first is that when we have small data sets, like 20 values or fewer, that we should just use a table instead of a graph to share that information. Also, that the graph of data should make us focus on the true nature of the data, not on other elements. So this is a place that pictographs a lot of times fall short. So eye-catching but distracting design features, those are not necessarily great. Right? Also, like bar graphs that are choosing to use those 3-dimensional bars instead of just a regular bar, it's failing on this front. Also, we should make sure that we're not distorting data. We need to construct a graph that reveals the true nature of the data. So we don't have these area versus volume versus length things happening. Or we don't have our vertical axis not starting at 0. Or we don't have a pie chart that doesn't have wedges that are representing the right percentages. And finally, almost all of the ink in the graph should be used for the data and not the other things around it. So we want to go and really focus people on the important part, and the important part is the data.